Okay, so we are in an introduction to statistical learning. We're in chapter 4. We are just starting the applied questions in chapter 4. We're on question 13. Okay, so I'm going to do all of this in R, and so you can get to the Colab sheet and look at the R code, or you can look at the R code here. I've also done this in Python in a different Colab sheet, where again the link is in the description. I don't think I'm going to do videos for the Python. One, because the code tends to be a little bit more convoluted, and so I feel that I'm just duplicating my efforts with something that is maybe more clearly explained in R. If you hate this, then I guess tell me, and then if there's enough people that suggest that they want Python, then I will start doing Python again. So anyway, so this is a long question, parts A through J, and so we'll take them in turn. But what's important here is, or what's important to all of them, is that we're using a data set that is part of the ISLR2 package, which we will load momentarily, and it's called weekly. And this data set is very similar to the data set that is used, or a data set that is used earlier in the chapter called Smarket. Okay, so we'll look at the data set here in just a moment. So first thing, so let's go to A. Let's go to A. Okay, well, first thing we want to do is to load the package. Okay, and so that's what I've done here. I've already loaded it. And then I am just changing the name of the data. It's called weekly. And I'm going to change it to D just to reduce my typing. Okay. So part A is we want to produce some numerical and graphical summaries of the weekly data set. Do there appear to be any patterns? Okay. So I've already loaded the data, and so here I have the head, the first 6 rows of the data. Okay, so let's just take a look at it. So we have the year that this is taking place, and then let me go over here to today. And so today is a weird name for this because it's actually what happened this week, not what happened precisely today. But we get values, and these values represent whether the market went up or down and by how much. So here the market went down by negative 0.27 points or percentage. Okay? And here it went down 2.576%. Here it went up 3.5%. Okay? So whether it's going up or down in the today part is denoted with the negative or no negative. And then that information is made further explicit when we go to the direction. It either went down, negative 0.27, or up 3.5. Okay. And then we have all of these other predictors over here. So we have lag 1, lag 2, lag 3, lag 4, lag 5, and as well as volume. So let's take these in turn. So volume, I believe, is just how much stocks are being traded on that day. Okay. And now, so lag 1, so if I'm looking at today, lag 1 is what happened yesterday with reference to whenever this measurement was taken, 1 time unit ago, 1 week ago in this case. Lag 2 is what happened 2 weeks ago from when this measurement was taken. Lag 3 is 3 weeks ago from when this measurement was taken, and so on, all the way up to lag 5. Okay. The reason that I know what is being represented by these variables is because I can call up the data file on or the information file on weekly, right, with question mark weekly, and if I do that, I get all this stuff pulled up. That tells me what the different variables mean. Okay, so we're supposed to produce some summaries, some numerical and graphical summaries. So one way that we can produce these summaries is with the summary function. Okay, if I run the summary function, I get a little bit of a printout for each of the variables. Okay, so for instance, if I go to today, I get the minimum value of today, so that would be the biggest drop, as well as max, which would be the biggest gain. And I get a median and a mean, etc. Okay. Now, one thing that is missing from the summary output is that might be useful is something like a measure of how do I want to say this, of spread. So we kind of see the spread here because we have first quartile, median, third quartile. Right, so you can kind of see how how everything is distributed, but another measure of spread would be standard deviation, and that's not part of the summary output. So we can also get that by using the apply function. So I'm going to use apply, and then, so this is the code for it, and I'll explain it. So it says, I want you to apply a function. What is that function? It's standard deviation, SD, and I want you to apply it to the data D. Now, do I want to apply it to each row or to each column of D, right? Because remember, this is what D looks like. Well, I want to apply it to each column, right? So I want to know what is the standard deviation of lag 1, the standard deviation of lag 2. And so column is encoded by 2. If I wanted the row standard deviations, in this case it wouldn't really make a lot of sense, but in other contexts it might, right? Well, then I would put 1 there instead. Okay. So anyway, so that's how we can get some summary. We might also want to look at relationships among the different variables. And so one way we can do this graphically is with this pairs function, pairs D. And so that produces a plot like this that I'm going to try to expand here. Okay, so here's my pairs plot. All right, and so the way to read this is each one of these, so along the diagonals is each variable in our data set. And then each one of these plots, little subplots, is all of the data points with where the x-axis is the variable, vertical in orientation, and the y-axis is the one that's horizontal in orientation. So, so for instance, if I wanted to know the relationship between volume and today, the variable today, where volume was the y variable on the y-axis and today was on the x-axis, I would go here. Okay? If I wanted the inverse of that, I wanted today to be on the y-axis and volume to be on the x-axis, I would go here, right? And you see that these are kind of, I don't know what the right word is, but 90-degree rotated versions of one another. Similarly, if I wanted to look at the relationship between, say, volume and lag 4, where volume is on the x-axis, I would go to volume, I would go up to lag 4, right? And so that would be represented there. Okay, so that's fine. But we could also do something a little bit different. So instead of getting just these graphical visual displays, I could also get like the correlation coefficient. Okay, so I'm going to use we can get any correlation coefficient that we want, but I'm going to find the Pearson correlation coefficient, right? And the way that I'm going to do that, there's different ways of doing it, but I'm going to use a package called coreplot. Then I will call the function coreplot, okay? And well, this is the rest of the code, and you can kind of play with it to see what happens. But I get an output that looks like this, where so every box here is the correlation coefficient between two variables. What two variables? It's the one horizontal and the one vertical to that box. So for instance, this negative 0.07 is the correlation between lag 2 and lag 5. Okay. Of course, along the diagonal is lag 1 with lag 1, lag 2 with lag 2, and so they're all 1, right? The correlation with itself is always 1. Okay. And we're also asked to look for some patterns here. Well, there's some interesting things. Maybe the most interesting is there's not a lot of strong correlations here. Okay. Everything really is right around 0 correlation. And that is maybe interesting. So this is not on economics, and nor am I an economist. I'm not an economist. But I think that there's something called like the efficient market hypothesis that basically says that in a market where a lot of people have a lot of information and a lot of common information, it's really hard to gain an advantage, because any advantage that is there is immediately observed and acted upon so that it dissipates very quickly, right? And so if there was you would expect that if there was a strong pattern in here, that it would already be utilized, and so the pattern would be diminished and diminished and diminished. There might be some pattern where there seems to be kind of oscillating up and down correlations, positive and negative, kind of, sort of. If you squint your eyes, I mean, it's not a perfect pattern, but something like that might be in there. Okay. Okay, so now we are on to part B, and here we're going to use the full data set and perform logistic regression with where we're regressing direction, up or down, on the different variables, okay? Lag 1 through 5 as well as volume. Okay? So this is the code for that. Okay, so I'm just regressing direction on the other variables. Direction is a binomial variable, so this generalized linear model is binomial, and the link function is logit. Okay, if you're not familiar with link functions, this is not really the place for me to go into that, but you should look it up. So I have other videos on generalized linear models and other playlists. There's probably even better resources than that because I'm always just responding to questions in textbooks. And so anyway, but you might want to, if you're not familiar with that, to look it up. Okay. So anyway, so we can run this and it's going to give us some output. And what it's going to be telling us is how each of these variables is affecting the log odds. Okay. But the log odds of what? Okay, the log odds of direction being up or the log odds of direction being down. Okay, and so in other words, we need to know how up and down are being encoded by the model. All right, and so to do that, we can use this contrasts function. Okay, and we see that that it is encoding down as 0 and up as 1. Okay. So, so what this means is that when so here's the summary function right here. So that means that that all of these are pertaining to the log odds of the market going up versus going down, or in other words, so remember odds is a ratio, right? And so the ratio here is the probability of going up versus over the probability of going down. That's what these different values represent. Okay. All right. So now we're asked to decide which of these is significant. Well, there's only two that are significant. One is intercept, and the other is the lag, or I'm sorry, is lag 2. So let's think about what these mean. All right. So if the intercept is significant and it is a positive value, it doesn't really even matter that it's significant, but here that's kind of an arbitrary threshold before we take it seriously, I guess is one way to think about it. But a positive value means that the log odds of going up are positive. Okay, so the fact that the intercept is positive suggests that there is a general disposition of the market to increase, to go up. Okay, so that's kind of an interesting observation. The other observation here, of course, is that lag 2 is the only significant predictor. The intercept isn't really a predictor, and it's also positive. So in other words, so the way to read this is that the log odds of the market going up versus going down is affected by lag 2, such that a 1 unit increase in lag 2 causes an increase in the log odds of this value right here, 0.05844. Okay, so that's interesting, but it's hard to think in terms of log odds often. Okay, and so one thing that we could do is we could just convert this quickly to odds, right? So if this is the log odds and we want just the odds, we need to reverse the log, and so we do that by exponentiating it, right? So we get this. Okay, so we take the exponent of the coefficient. Okay? So in other words, now this says that the odds are increased by, by about 6% for a 1 unit increase in lag 2. Okay. Now, what if there's a 2 unit increase in lag 2? It wouldn't be 2 times this. Instead, it would be this squared. Okay, so it would be this. Okay, and what about a 3 unit increase? It would be 1.06 cubed, and so on and so forth. Okay. All right. So now, with what we just did, we want to compute the confusion matrix. Okay, for all of this, and so first I'm going to get the probabilities of being up or down according to the logistic regression here. Okay. So I'm predicting from this regression that we just ran, okay, and I'm trying to get a response. So in other words, what type of prediction? Well, I want to know what is predicted to happen, whether it's going to go, the probability of it going up, basically. Okay, and so that will give me values that represent more or less the probability of it going up, of the market going up. And then I'm going to set a threshold that whenever that probability is greater than or equal to 50%, I'm going to say that that's a prediction for up. And so now I use the table function here. And so I'm using my predictions versus what actually happened. And then this is the confusion matrix. And so the way that I want to read this, when the model predicts down, it is actually down 54 times out of 430 plus 54. Okay. Similarly, when the model predicts up, the market actually goes up 557 times out of the 557 plus 48 times the market actually went up. On the other hand, when I predict up 430 times, I am wrong, right? So I predict up 557 plus 430 times, and I'm only correct 557 of those times. Okay, and so you can kind of look at all the permutations, and I've kind of spelled those out down here. Okay. All right, so now we kind of get into the more interesting part here. So we're going to repeat the logistic regression, but we're only going to use a training set of data, and we're defining the training set of data as things that happened before or at the year 2008. Okay, so everything that happened 2009 onwards is going to be our testing data. Okay, so this is how I make my training data, right? So I set up an index, and so I say any row where the year is less than or equal to 2008, call that training data. Otherwise, call it testing data. All right, so I'm going to do the same thing that I did above. This is the same regression that we already ran, but now my data is detrain instead. Okay, so and by the way, we're only using lag 2 as our predictor. Okay, is our only predictor, because not that this logic necessarily follows, but roughly what the book is asking us to do is to just take the significant predictors here, maybe just to simplify it. Okay, so anyway, so we can get the summary, but that's not really what's going to be interesting here. What we want to get to is, again, the confusion matrix. Okay, so I just use, so I'm calling it logit confuse, and it's the same code that we had above. And so here, so notice that we have a smaller amount here because I am predicting. Okay, so I'm predicting using the model, but with new data test. Okay, and again, so I'm going to get different probabilities of the market going up or down, and anytime it's over 0.5, I'm going to call that going up. And so using that rule, this is my confusion matrix. Again, when I predict up, the market goes up 56 times. Okay, out of the, 61 times it actually goes up. But when I predict up, I am only right 56 out of 56 plus 34 times. So I'm wrong that often. Okay, so anyway, again, you can look at all the different permutations here. I've tried to spell some of them out here. Okay, but now we're just going to repeat that using LDA. Okay, so I'm using LDA here, and I get my confusion matrix. In this case, you'll notice that the confusion matrices are the same for the two. All right, so between logistic regression and LDA. Now I'm going to use QDA, and QDA always predicts up, actually, which is interesting. Okay, but this is that confusion matrix, so it never predicts down, so it doesn't even have a predict down row, which is fine. Okay, and we also do with k nearest neighbors. All right, you can see the code, and this is the confusion matrix. And then we also use naive Bayes. Okay, so again, you can look at all that, confusion matrix. All right, so now the last, well, there's really two final parts, but part J just asks us to experiment with all of these different models, and I'm not going to do that. I'll just let you do that because there's, it's meant to explore different things. But part I is kind of interesting. So it wants to ask, so we need to know which of these methods is providing the best results. Okay. The question here is, what do you mean by best? What qualifies as best? And I think that what qualifies as best depends on what are you valuing. So for example, so if you're using these models to say bet on the stock market, okay, it could be the case that when you correctly predict up, so you predict up and the market goes up, that you stand to gain way more than you stand to gain if you predict down and the market goes down. Okay, so in that kind of a scenario, you'd want the model that predicts up, that correctly predicts up more than the other models. Okay, but it could be something different. It could be that when you incorrectly predict down, right? So you predict down and it goes up, you just lose a little bit of money. But if you predict down or you predict up and the market goes down, you could lose a lot of money. Okay, so in this case, the model that you would be looking for is the one that's making the least incorrect predictions of the market going up. I'm confusing myself here, but hopefully that makes sense. Okay, so I'm kind of spelling that out here, and there's probably going to be times where you don't, that all you care about is gains or losses, right? If gains are virtually unlimited, or if losses just threaten to completely ruin you, take you to zero, then in those situations, maybe all you care about is gains, or all you care about is losses, and now the model that is doing best is the one that aligns with making the most correct positive predictions, or making the least costly losses predictions. But probably most of the time you're concerned about some combination of gains and losses. Okay, so for example, let's say that that our correct predictions gain us $2, but all losses lose us $1. Okay? Well, then what we want to do is we want to play those scenarios out, right? So you can do that with this code, but so I'm going to take 2 times my correct predictions, which is just the sum of the main diagonal of my confusion matrix. So in other words, it would be down, down, up, up, minus the I don't know what that is, but the opposite diagonal is what I'll call it. Okay, and so we can do that with this code here. Okay, and we could do it for each model, for the logit, for the LDA, QDA, KNN, K nearest neighbor, and naive Bayes. Okay, and so when we do all of that, we get these expected values, or expected gains. So in this case, logit and LDA are performing the best. Okay, but what's performing the worst here? Well, QDA is apparently performing the worst. Okay, but we could make even more complicated scenarios, right? So it could be that true down predictions gain us $5, true up predictions gain us $1, false down predictions lose us $2, and false up predictions lose us $1. That should be S. And again, you can just go through and you can play out all of these different scenarios. Okay, so in this case, it just so happens that again LDA and logistic regression end up doing the best, but now the one that does second best ends up being K nearest neighbors. Okay, for instance. So I think that the correct answer to this part I is which one is doing the best. Well, it depends on what you value. Okay, and once you say what you value, then you can determine which one is doing the best. I think that's probably the right answer. Okay, let me know if you disagree. Okay, this one has been way too long. I'll let you go.